So this is a video for page 71, number 5. Question is general relationship. Show that if f and g are continuous on a to b and c to d respectively, then this relationship holds. All right, so the first step would be, I suppose, to just kind of dive right in. All right, so let's focus on the left side. The innermost part of the iterated integral. All right, we're integrating with respect to y. So if I take the antiderivative of the sum, it's going to be the sum of the antiderivatives. So I can look at the f of x. That's a function of x. Its antiderivative would be f of x as a multiple of y. Now, that'll be integrated over the interval of c to d, or evaluated, I should say, over the interval of c to d. The other part I can't do anything with just yet. All right, so I'm just going to leave that as the integral from c to d of g of y dy. Now, if it was just the antiderivative of lowercase g of y dy without the bounds, then I would call it capital G of y and call it a day, but that's not the case. So I now need to integrate that result with respect to x. So really it's the next level. Or the next iteration, if you will. So I can just tack on a to b here, dx at the end, and just kind of carry it through. All right. So you'd be focusing on these two things separately from one another. All right. One of them, just like before, I wouldn't be able to really do anything with, but the other we can do a little something. All right. So if I integrate with respect to x, the function of x. All right. So, oh, apologies. I never evaluated before I get to that. Show the next step before I do. Yeah. So this is over the interval of c to d. It's with respect to y, so I can pop it in. I can simplify. So brain cramp. So d f of x minus c f of x plus all that other stuff. So a to b dx, and now I can evaluate it for each piece. The issue that I'm going to run into, again, is the fact that for the right-hand expression, there's really nothing I can do. All right, but for the left one, I can go through the process of integration. All right. So what I'll do, or at least justify using integration. So what I can do is I can factor out an f of x. So over a to b, f of x times d minus c dx plus, and just make sure I got everything here, a to b, and then I still got this guy, c to d, g of y dy dx. All right. So at this point, the best I can do is pull out that d minus c. So I'm going to get a little slick here. A little copy paste action. Move this. Collapse it down. And throw this in front. So, it doesn't look like we got anywhere, but believe it or not, we actually accomplished the first objective, right? Because this, let me highlight it in red, this whole shabiggity bangity boom was equivalent to the original expression, and that's what we have here. So then it kind of begs the question, all right, cool, wonderful, how do I get the other one? Well, you see in that case, it looks like the dy was isolated, or at least the y function was isolated. And that happened because the order of integration changed, right? So the base region here is rectangular. So what I can do is do a little switcherooski here and make my original integral, my original iterated integral, go from c to d, a to b, so swapping the bounds. Still the f of x and g of y, but if I want it in the order that they have it here, I might want to make my life easier by taking advantage of the commutative property and just doing a switcherooski right up here. So basically swapping everything. Right, so then dx dy. And so working inside out, I'm going to shrink it down a little bit. Try to stay with a similar color scheme, if not exactly the same. So we got this guy right here. If we look at it a piece at a time, it's with respect to x. So g of y will act as a multiplier, constant multiple. So that'll be a constant multiplier of x over the interval. Now that came through. That's shocking. A to b. I did it all in orange. So plus the integral over the interval of a to b of f of x dx, which is not something we could really do anything with just yet. Now, I'm not going to forget the next step this time. Purple. I mean, I was staring at it. You'd think I'd be able to figure it out. So replace the x's with a b and an a. So b g of y minus a g of y plus a to b f of x dx. I screwed up the color scheme, so I'm just going to kind of bag it at this point and just kind of go with what feels right. So I'm going to factor out a g of y. So it becomes b minus a times g of y. And now I can apply the next iteration, which is the whole shibiggity bangity boomity boom. Really just means that we're integrating over the interval of c to d dy. So we're looking at this guy and this guy separately. So we would have, I could factor out the b minus a. C to d of g of y dy plus the double integral from c to d, then a to b of f of x dx dy. And if we compare that with what we have above, you see it is precisely identical. Doodly doodly. All right. And so there's your proof. So all three of these quantities are exactly the same, mathematically and symbolically. Well, symbolically they're not the same. They look different, but mathematically they are. And there it is. That is page 71, number 5.